All right, so again, sorry for that. I already know that it's 1 minute remaining left. It's just that I wasn't anticipated that uh, wala na pala. Okay, so it's not 1 minute anymore, but it's like 5 seconds remaining left. So it's quite, it forcefully closed our first meeting. Well, anyway, so any questions so far regarding with this circuit diagram? Questions or clarifications? Okay, so guys, none anymore. Anyway, so let me just check if you guys are already in front of your computers. So just give me a thumbs up. Okay, very good. It's like 16 out of, or 17 out of 19. All right, so let's now proceed with the explanation. So again, we have this flow of circuit. So from here to D2, and then this is now open since okay, they are in reverse bias. So it will flow on our resistor and then will flow here and then we'll go back to our voltage input or the voltage source itself. So as a result, we have a reading of VO is equal to Vin if this one is an ideal diode. Okay. And the same with the negative cycle. So we have a flow of current from here going to D1 and then going to VO and then going to D4 and then we'll go back to the voltage source itself. Okay, so the same explanation and what we have on the positive cycle. Okay, just apply that one with different polarity. Okay, so as a result, it also accepts a negative cycle. And since they accept, both positive and negative, you can just draw them, okay, into something like this. So of course, the first one is positive, and then the second one is negative. So don't get confused with this one. This one is the negative cycle. Okay, it's just that it was placed on above so that we can draw a line right here, and then we could just see that this is the average, okay, reading of this one. Okay, where in the VDC of a full wave rectifier is a 0.636 multiplied to VM if we have an ideal diode. So if you guys are going to take a look on the VDC, okay, of our half wave rectifier, so it's just 0.318, but in full wave we have 0.636. So in other words, just double the value of 0.318. Okay, so it's like, passing through one diode is 0.318 voltage drop, but passing through two diodes, so let's say D2 and D3, will give us a voltage drop of 0.318 plus 0.318 is equal to 0.636. Okay, so that is the DC reading, okay, when it comes to a full wave rectifier, or specifically the 4-diode bridge rectifier. Okay, so of course you can add more, like you can have 2 diodes on this one and then another 2 diodes on this one. But then again, okay, so you'll have higher voltage drop and then you'll have a lower voltage or average DC output. Okay, so yeah. And then the next one is now if we have a voltage threshold on this diode. So again, same scenario. Okay, so just deduct that a voltage drop or voltage threshold. So we have the V peak value or the voltage input, and then since it will pass through two diodes, so two negative 0.7, and since they are two the same diodes, so silicon and silicon, so you can just say negative twice of VT. So you cannot apply this negative 2 times VT if we have different diodes right here. Let's say the first one is silicon And then the second one is germanium. So as a result, this one now is exactly -1 volt. Okay, so it's not twice of VT anymore. All right. So are we clear so far regarding with this one? If we have a voltage threshold, what about the others? Any question or clarification so far? Okay. So it's like 30% to 40% of you were able to get this one. Okay then, so let's have an actual example. So let's say using silicon diode in full wave rectifier. So as depicted in the above figure, if instead of a yield diode, a silicon diode is used, applying Kirchhoff's voltage law over the conduction line would give us the following result. So again, you don't need to memorize these formulas. So VO is equal to is equal to VI minus 2VT. So you can just simply apply Kirchhoff's law, okay? So from here to there, from here to there, and then going back to the VI, you will have this kind of formula. And then if you're going to simplify this one, you will have this formula. VO is equal to VI minus twice of VT. Okay. And then for the VP or Vmax, so it's of course VM minus twice of VP. So it's actually similar with this one. Okay. So are we clear so far on how did we get this equation? Okay, so just let me know if you guys are quite confused and sir, why do we have that kind of equation? So again, you can just simply apply Kirchhoff's law or Ohm's law, and then you will get that kind of equation. So again, as usual, your VI must be greater than twice of your voltage threshold, okay, in order for you to run that circuitry. Okay, and then here's the formula again for the VTC. So let's talk about tagal naman ng real example natin. So I mentioned a while ago that we're going to have a example. Anyway, so let's talk about PIV and PRV first before maybe next slide pa yung mga examples. So PIV and PRV are just the same, just different terminologies. PIV stands for peak inverse voltage, and then PRV is the peak reverse voltage. Okay, so in other words, it is a voltage, okay, at a reverse bias connection. So if we have this peak value on the positive or in forward bias, of course, we also have this peak value on a reverse bias. So we call that one peak inverse voltage or peak reverse voltage, okay? But you can only get this kind of result, this reverse bias voltage, if we have a, exceeded value of your diode, or if you have this so-called Zener diode, okay? So if you have that Zener diode on your circuitry, that means that it allows to have a breakdown voltage. So what is that breakdown voltage? So meaning once it exceeded that certain amount of voltage or that threshold of that voltage, okay, so it will go into a breakdown, okay, wherein we call it one Zener avalanche region. So as a result, it will now allow a flow of current on that diode. Okay, so that is the one that we call the so-called leakage current. Okay, because supposedly it won't be able to pass through that diode, but since it is really made for that situation, wherein once it exceeds a certain value on a peak inverse voltage, okay, or a reverse bias voltage, it will permit a current, okay, which is called the Zener avalanche region. All right, so here is the scenario, okay, if ever that you have that peak inverse value, okay, so you can only attain that one if we have this open circuit or a reverse bias connection. Okay, so for now we don't have real example for this one, so we will talk about this one in finals, okay, the Zener diode. But yeah, the PIV rating must be greater than or equal to BM. Okay, so mostly, of course, it's always higher than the VM. So if we have a peak value of 20 volts in peak inverse, so there's a big possibility that we have negative 30, negative 40, or negative 50. Okay, so we don't have an equal voltage input. So we have a consistent, let's say, positive 20 volts, okay, on the positive cycle. But at the negative part, so we have a consistent of negative 50. So 20, 50, 20, 50, 20. So something like that, okay? So, okay, so just continuation for the PIB. So this is where you read, okay, the PIB reading. So if we have a forward bias, okay, so this one is your V peak value, okay, on the middle one. And then if you're going to read the peak inverse voltage, so of course, it will be at this point. Because again, you can only attain that one if we have a reverse bias connection. So this one or this one right here. Okay, so let's have now a real example when it comes to a full bridge rectifier. So determine the output waveform for the following diode network, and also calculate the output DC level and the CPIV for each diode in the network. So I'll give you guys a minute to analyze this circuit. So we have this voltage input right here at 10 volts, a peak-to-peak voltage. And then what will happen if we have this kind of circuit? So let's answer the waveform first. So will this accept both, or will this accept a positive cycle only or a negative cycle only? Anyone? Okay, so let me ask someone. So it's okay if you're going to have an incorrect answer. Mr. Bradley Mina. Mr. Mina, are you around?
Yes, sir.
Okay, so what do you think? What is our waveform if we have this kind of circuit right here? Will it be positive only, negative only, or both?
So I'm just gonna guess, but I was gonna say negative only.
Negative only. Okay. What about the others? Do you guys have another assumption? Or do you have the same answer as Mr. Bradley Mina? Okay, so let me ask another person. Mr. Santa Cruz. Are you around?
Sir.
So,
yes, sir.
do you agree with the answer of Mr. Mina?
Sir. 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 Siguro, sir, positive only, sir, para maiba.
Para lang maiba. Hula ko, wala kang idea, no, kung paano. Positive only one. Okay, so you have two. Dalawa na kayo. Okay, so there's two of you now who has an answer positive only. Okay, so the three of you are actually incorrect. Okay, so if you guys are going to take a look on this one, so you can, have a step-by-step scenario wherein, let's say, of course, we have the positive negative connection first, wherein we are still at the positive cycle, which is positive 10 volts. So we have positive 10 volts right here. Okay, so the first one is positive negative, so this will be turned on. Okay, so say idea is what we have in the full wave rectifier. And then this one is now a up, since we have a positive to negative and then negative to positive. So reverse bias. So as a result, for the positive cycle, it will flow right here, and then it will flow right here, and then it will split into two, since we have the same flow. I mean, we have the same value of resistance, and then some will go here, and then some will go here, and then they will meet again right here, and then as a result, we have the 10 volts right here. Okay, so the same scenario if we have the negative cycle. Okay, so in here we have negative 10 volts. So erase this one for now. Okay, this will become negative and then positive. So if we have this flow of current, so we have negative to negative, positive to positive, so this will turn on. And if we have negative to positive and then positive to negative, so this will turn off. So as a result, it will only flow in this diode. Okay, so some will go on this side, and then some will go on this side. And then this point, then will flow here, and then they will meet again right here. And then we will have a reading of negative 10 volts. Okay, so that is why this will accept both positive and negative cycle. Okay, so this is actually your hint already when it comes to a full wave output. Okay, so in here, it will just differ when it comes to the voltage output, since we have a different approach when it comes to a full wave we have full wave waveform, but we don't have the same value for the VO. Okay, so yeah, okay, so it wasn't mentioned here to solve the voltage output also, but anyway. So it says recalculate the output DC level and then the safe PIV for each diode. So let me just show you guys the step-by-step solution. So here is the solution for the positive half cycle. Okay, so this will open and this will be closed, and then it will on this side. And then for the negative half cycle, so same scenario. I think I wasn't able to show the negative part. But yeah, same scenario. So this will be open, and then this would be on. Okay, so we have a positive and negative cycle. But in here, as you guys can see, why we only have a voltage output, okay, of 5 volts. How did that happen? Why is that we don't have a 10 volts reading anymore? Anyone who can explain why we only have 5 volts reading? Why not 10 volts? Okay, let me ask Miss Paklaw na. Miss Paklaw na. I guess she's not around. Okay, what about you, Mr. Maaba? So Mr. Maaba is not also around. What about you, Mr. Aral or Aral? Mr. Nathan?
Sir, na-divide yung sa 1 na yung 10. Or
Na-divide sa 2, yes. But bakit siya na-divide? What is the reason behind that? Okay, so let me answer this one. All right, so in here, remember what I said in circuits 1. So this resistance right here, this one could be replaced by a RL or load resistance or any appliances in your home. So you can actually place it right here, RL right here or RL right here. But the most ideal one is, you have to place it right here. So when, well, only if you have this kind of circuitry. Okay, why? So if you want to have a reading of a positive and negative at the same time, okay, so you have to place it right here, not here, and then not here. Why? So in here, if we have positive 1, so it will flow, it will still flow here. Okay, but if you have the RL right here, okay, you won't be able to read the negative part anymore because it will only flow at this part and at this part. Well, some of them will still flow, okay, but after passing through this RL already. So in other words, your resistance is already divided into 2, and then it will be divided again into another one. Let's say, same lang pala. But yeah, of course, you will have another voltage drop. Okay, since it will pass through another wire, so we don't know how many voltage resistance you will get from passing another wire. Okay, yeah, since directly naman na siya dito, okay, it's already directed here. Since if we have a negative reading, this will become off. So it won't split into 2, but it will still flow here. But anyway, so we could place it right here or right here, but the most ideal one is on this RL right here. And then the reason why we only have a 5 volts reading. So if you guys are going to take a look on this one, the VO or the RL itself, okay, is being read at this point. So if we have a 10 volts reading at this point, okay, so it will split into 2. So some will go here and then some will go here. And then basing on the value of your resistance, you have the same values. So as a result, just divide that 1 into 2 since it will equally go on the other side and then on the other side also. Okay, so the result of this one will not be equal if we have different values of your resistance right here and then the resistance right here. Okay, but since we have 2 equal resistance, so it will be divided into 2 perfectly, which is a reading of 5 volts right here and then another 5 volts right here. And we will pass through here and then will be added again as another 10 volts. Okay, so were you guys able to follow on why we only have a 5 volts reading on the VO? Why not 10 volts? Okay, so just be mindful, where is this VO being placed? So of course, if our VO is at this point, say we have a positive, negative VO right here, then of course we have a reading of 10 volts. Okay, since all of them, will meet again into one place. Okay, so yeah, that's the reason why we have a 5 volts reading right here. So this is another approach, but I think this one is a little bit more confusing since if you guys are going to take a look at this one, it's like, this is now 4 kilo ohms if you're going to add them just in case. And then we have 2 kilo ohms right here. Well, of course, if we are, if you are the current itself or if you are the voltage itself, you will only flow on the lesser voltage drop or lesser resistance. But yeah, at this point, they will already split into 2. So some will go here and then some will go here. So 5 volts reading on the VO and then 5 volts will go here. Okay, and then this is the solution for the negative half cycle. So we have the positive half cycle, which is 5 volts. So of course, we also have a negative 5 volts reading. Okay, and then the absence of 2 diodes in the bridge results in the reduction in the DC output with a magnitude of 3.18 volts. So you can use this formula, okay, so 0.636 times 5 volts, or if you want to get the VI itself, okay, so 0.318 times 10 volts, okay, so this is for the first one, and then the same for the next one, okay, which is negative 3.18 volts. Okay, so we have 2 separate reading for the average, okay, but overall, if you want to get the whole of it, so we have 5 volts, 5 volts, 5 volts, 5 volts, regardless of the positive or negative. So you will get 3.18 volts. Okay. So are we clear so far on how did we get the VPC, the VO, and then the waveform? Oops. So just let me know if if you're confused maybe, or if you need more explanation why. Then, so if you don't have a question anymore, then let's now proceed to the center tap full wave rectifier. Okay, so in here it's just so it has a lot of explanations. So I will leave the reading part to you guys. I will just mention the important things when it comes to a center tap rectifier. So a center tap rectifier is a rectifier also wherein it converts AC to DC. Okay, so it has the capability to increase, okay, or decrease the AC voltage. So if we have a 20 volts on the primary winding, okay, we can have a 40 volts secondary winding. So it can double, or sometimes it could triple, depending on how many inductance you have in here. So in other words, the more inductor that you have in here, the more that it will amplify your voltage. Okay. And then this one is called center tap. That's only because the reading, okay, is placed on the middle of your inductance. Okay, so this is the wire which is being tapped on this inductance. So it's called center tap transformer. Okay, so let's have the full circuit, okay, of your center tap rectifier. So we have this voltage input, of course, the positive and the negative. Okay, and then we have the peak-to-peak value. And then in here, we have the primary winding and then the secondary winding. Okay, so we have the V1 and then V2. So V1 is the positive cycle. And then V2 is the negative cycle. Okay, so again, this one will give us a positive and negative output. Okay, so the same as our input. But then it has the capability to convert this one into a DC. So when I say DC, it's like a pure DC already. Okay. So how do we do that one? Just add a capacitor somewhere around here, and then you will get a smooth DC output. But since we are still in AC, let's talk about AC only for now. So you will have that kind of say call this one that kind of example or that kind of experience. Okay. Once you are now in finals. Okay, because we'll only talk about that one in finals of laboratories. Okay. All right. So anyway, if you're going to add B1 and B2, you will get the B total, of course. Okay. And then CT stands here for the center tap. Okay. So any other important thing? Okay. So one more thing. So in here, V1 and V2 are equal in magnitude but opposite in direction. Okay, so when it's the opposite in directions, of course, we have positive cycle, negative cycle. So in other words, it is 180 degrees out of phase with each other. Okay, so however, by using a full wave rectifier with a center tap transformer, we can produce the voltages that are in phase with each other. So in other words, instead of having a positive right here, negative right here, positive right here, and the negative right here, you can actually put them in phase or in one direction only. So if we have positive cycle, they can actually place it right here, okay, on the negative cycle. So if we have two values at one direction, so they will be added with each other. So that is why it has the capability to amplify your initial voltage. So if you have a VI, which is equal to 20 volts, okay, so in here, since positive and negative were combined with each other, so we can have a V peak or V max of equal to 40 volts. Okay, so that is one characteristic of a center tap rectifier. Okay, so anyway, more explanation when it comes to center tap. So I'll skip that one. Same with this one. So we can also read this one on how this center tap full wave rectifier work. So this is the positive one, and this is the negative part. Wherein, of course, if we have positive cycle, then we have a reading right here, and then we have an open circuit right here. And this is for the negative cycle. So vice versa, we have a reading right here, we have an open circuit right here. Okay, and as a result, we have this one. So if they are, or if we have this AC input, so we have this D1 current. Okay, so positive, 0, positive, 0, positive, 0, positive, 0. And then for the D2 current, so we have 0, negative, 0, negative, 0, negative, and so on and so forth. And if you are going to combine them, of course, you will have a full wave waveform. Okay, so positive, negative, positive, negative, positive, negative, and so on and so forth. Okay, so as you guys can see, this one is similar with the 4 diode bridge rectifier. It's just that it's only using 2 diodes instead of 4. Okay, and then of course, it's now using an inductance or inductor. Okay, so in a 4 diode, you don't need a inductor, but in a center tap rectifier, you need this one to make this one work. So are we clear so far up to this point? Am I too fast? So yeah, because most of them are just explaining the connectivities, and then explaining how does the positive cycle work and then the negative cycle work. So again, any question, guys, before we proceed to the last example? Okay, so it seems that there is no question anymore. Okay, so here are just, you know, the like the conclusion or the realizations when it comes to a center tap rectifier. So again, I will leave the reading part to you guys. This one is also the same, you know, with the full wave rectifier. So it says here a small voltage is wasted. However, this voltage is very small as compared to the voltage appeared to at the output. So this voltage is neglected. So what is that voltage? So that is the voltage that is being consumed or eaten by your diode. So if it's silicon, it wasted a 0.7 volt voltage. And if it's germanium, then it's 0.3 volts. Okay. Okay, so let's have this last example. So example of a center tap fully rectifier. So solve for PIV. Well, it wasn't mentioned here to solve for the voltage output. And yeah, let me just show it right here. So we have this kind of circuit. We have the AC input, of course, which is a 10 volts peak to peak. And then we have here a 1 inductance only. And then we have 2 inductance in total. So as you guys can see right here, we have a ratio of 1:2. So meaning whatever is your input right here will be doubled. So if we have a 10 volts reading, so it can give you an output of 20 volts. So that is the reason why we have this 20 volts reading right here. So V2 is the voltage on the second windings, and then V1, okay, is the reading for the first winding. And then N right here is the number of your ratio and proportion. So N2 is the number of, let's say, if it's going to increase or decrease your voltage. So pedaling 1:1. So it could be 1:1 also, like nothing will happen. But in here, N2 is 2, and then N1 is 1. So it's 2 over 1, or it's now 2 times 10. So that is why we have a 20 volt reading for the V2. And then for the peak inverse voltage, so we have twice of your V peak. So in here, we have initial of 10, and then in here, you have a 20 volts, and then just double that one less your VT, okay, your voltage threshold. So we have this formula. So just use this one, 2 times V2 minus VT. So this VM is equal to V2 minus VT. So 2 times 20 minus 0.7 is equal to 2 times 19.3, which will give us a result of 38.6 volts. So that is the peak inverse voltage of the circuitry. So any questions so far? Are you guys able to follow? And why we have this value right here? Okay. So in other words, this 4-diode, okay, where is it one? This 4-diode bridge rectifier will give us a result of a positive and negative cycle, okay, or a full waveform, okay. But it doesn't have the capability to increase or decrease the value. Well, you can manipulate that one by, or yeah, you can decrease the value by, adding more components in here. So yeah, but if you want to increase, okay, or amplify the voltage, then you have to use a center tap full wave rectifier. Okay, so here are the formulas that you might want to check. So for the peak inverse voltage for the half wave rectifier, it's just the VM. Okay, for the center tap full wave rectifier, it's twice of the VM. So it has a double capacity, or it can manage twice of your VM for the peak inverse voltage. And then more than that, it's like avalanche voltage already. Okay, and then for the full wave, it's still VM. And then the other one is the average DC. So if you're wondering where did we get that 0.318, so this one came from this formula. So for the full wave, we have twice of VM divided by pi. And then for the half wave, we have VM divided by pi only. Okay, and here's the reference, and then that's it for the module 3. So 1 minute left. So if you have question, so just message me since we don't have enough time anymore. So thank you guys for coming, and see you guys after your midterm exam.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So if you have question, just message me, okay? Goodbye.